So with this example, you can see the car is moving downward on the inclined slope. This can be hill or slope. And this is kind of typical question or problem that we mostly observe with the basic idea of the Newtons. Since this car is not turned on any engine, so there's no driven force introduced. Only the force that acting on this car is its own weight, is mg. Since mg is in this direction, however, when you try to break the components of mg, you see the mg is here. If the incline is on this part, you can have the component that parallel to the inclination plane and the component that perpendicular to that inclination plane. So that can be like this component and this component. And the component that pulling the force that pulling this car down is this component, which is, you already know this angle as a theta, right? And when you try to making the right angle over here, this is theta, right? You have right angle here. This is like a part of right angle. When you compare to this triangle, you see the triangle over here. The theta over here is exactly equal to theta over here. That's why when you would like to break the components of the mg, you have the component of mg sine theta and mg cos theta. I will rewrite it. This is the mg cos theta when this angle is theta. So this is happen all the time on the slope or the hill like this, especially with this case on the IC driveway. The IC means you have the frictionless system. So this is freely moving downward due to mg sine theta toward the downhill of the slope. Since you have the direction of the force over here, you have the normal force acting perpendicular to the pushing direction, which is this part is your m. We write it like this: mg cos theta. With this motion, what you see here is this car moving with acceleration toward the downhill. So it looks like this. So you can redefine the axis. From this part of the system, you can look at the free body diagram and redraw it. And now you redefine your y-axis is slightly perpendicular to the inclined plane. And you have the x-axis parallel to the incline of this slope. Now you can make what I drawing here as my free body diagram to this kind like a particle or point like particle here. This is your car. This is your car. Now your car is spot and you have the mg sine theta to pull it downward toward x direction. It's had the mg cos theta due to the component breakout here that pushing the hill slope of the hill, and you have the normal force that acting on the different direction as equal in a magnitude of mg cos theta. So this is your free body diagram that you have. So now you like to find out the acceleration of the car. And as I said, on the IC driveway, you have the frictionless system. So your first job is to find A. How about this A? Okay, let's start like this. Now we arrange this here. For this case, you will apply the knowledge of the laws of motion or Newton's law. So you have a first one, if it's in equilibrium state, sigma F equal to 0. This is the first law of Newton. And the second one is sigma F equal to ma. With this system, if we look after individual components, we can see in y direction, there is no moving upward or downward. So that means if you look after y components, the sigma Fy is equal to 0. This is stationary equilibrium, or there's no result force along the y-axis like this. However, if you look after x components, you can see car moving along x-axis with the acceleration. Now x-axis is here, is like tilt or rotate axis. So what you got, the sigma Fy equal to ma. So from this relation, you can link to phi a from over here. However, not only the a that you can use the information from sigma Fy as well. So let's start from the x component first. If we look after x components, so look after x components. So what we have here, we have the this is not y, this is the x one, sorry. You have mg sine theta to pulling this direction. There's no friction because of IC path driveway. So this is only your resultant force in x direction. So you have mg sine theta equal to ma. So that you have your a equal to g over g equal to g sine theta. If you know theta and you know g on the earth is equal to 9.8 meter per second square, so you can find the acceleration in meter per second square out of this information. So not only finding the a, suppose you release this car from the rest, figure out about this on the incline and stationary plane. How can you further investigate to another information we will look after on the B part? So for B, if you said this car is moving from the rest state, that means the initial velocity is 0, and it's moving for a distance d. So it's moving to another point, like maybe for the sake of the space. So this may be initial point. You have u is equal to 0, and this is the point that you would like to find the terminal velocity. This is the terminal velocity that you have all the information this involved. But what is this problem asking you about is how long does it take the front bumper? So initially front bumper may be over here, and maybe at the terminal point, front bumper is here. Reach the bottom, and with this distance is d. You already know that your acceleration is equal to g sine theta from previous part, from the A part, right? So you will use this information, A equal to g sine theta, and investigate these. So what you have seen here, if you would like to know about the times that this car taken, you know the initial velocity, you know the distance, and you know about the relation. Think about the kinematics that you have learned. So you have 4 major equations, right? with 4 kinematics major equation, right? That they are v equal to v0 plus at. You can write this as u if you want, because initial velocity, you have the s equal to v plus v0 over 2 multiply t, or you can use with the s equal to v0t plus 1 over 2 at square, or v square equal to v0 square plus 2as. This is your 4 kinematics equation, right? Most of the way to solve motion of the particle, you can link between the knowledge of your kinematics in your first 3 chapters or 4 chapters, link to the Newtons, and then you can have the influence, which is you solve from sigma f x equal to ma. This is the cause of the effects, right? And link to the result. This is part of the result. Whether you would like to predict the velocity, the initial or terminal, acceleration, displacement, or the time. And these are the results of the course. As I said, this is your dynamics point of view, and this is your kinematics point of view. So what I'm teaching you is not only how solving just this problem, but how to solve any general problem using the Newton's and 4 major kinematics equation. So now let's move to what it's asking for is how long does it take to moving here, and what is the speed it arrived there. So you need to determine the time for the first step, and the second step gonna be about the terminal velocities. With this case, because I don't want to squish everything up, I will move to another slide with the key information that we want. So for the first one, if we would like to determine about the time for the first question, how can we find it? And if we would like to determine about the terminal velocity, how to find it? It's not 0, sorry. Since we know initial velocity is 0, we know the distance is d over here. We know the acceleration from the part that we solve is g sine theta. So in order to determine the times in A, so what parameter we already know? We know the displacement d, we know the initial velocity u, we know the acceleration a equal to g sine theta. So we can use the third equation of 4 kinematics equation, which is s equal to ut plus 1 over 2 at square. Because we would like to find the times, you can rearrange, you can sub in first if you want. Because we know u is equal to 0, okay, you sub u in, so this term is, you get rid of it. So if you like to determine the times, you rearrange this term, so you got t square equal to 2s over a. So with the square sign, to let you know it can be plus or minus sign, but with the time it's always in a positive or plus sign. So that you can find the time is equal to square root 2s over a. And you sub all the information in. I will maybe put here because we lack of the space now. T equal to root 2, and your s is d and a is g sine theta. So this is your time in second. Don't forget to put the unit after the quantity you try to quantify it or derive it. First part we did find about the time. If you know all these parameters, you can sub in, you can find time. However, if you would like to, in addition, however, if you would like to find the terminal velocity, which equation you like to use it? So now you got all the information, right? You know the displacement, you know the initial velocity, you know the acceleration is g sine theta. You know the time as well. Yes, equal to 2d over g sine theta under the square root. These are all information that you already know. So if I select the first equation, v equal to u plus at. So since you already know that u is 0, the reason that I'm using, because I would like to get rid of one term of this equation to reduce the term to less complicated, and it can be easier to solve. You can use other equation if you want, but this is what I'm chosen. So I'm get rid of the first one because I would like to find v. So I will sub everything in v equal to a, which is g sine theta, and t is square root 2d g sine theta. So this is kind of like square root up. So finally, you're gonna get square root 2d g sine theta for finding v. The unit of it is meter per second. I will write in the red colors so that you're not gonna get mixed up. So unit of time is second. Unit of the velocity is meter per second. Now in this case, we move to a two particle system, or you can define like this system more than one system. How different of this system compared to the previous one? You can see the interaction between each particle that happened, so that when you try to draw out the free body diagram, you can look at free body diagram as a whole system. The first one, I will write down the whole system, which is you have two mass, and look at they have only one, and with this mass represent M1 and M2. And you still have the resultant force F here acting into this system. This is your first free body diagram when you're looking after whole system. How about the second one? The second one, you look at individual particle. For this case, you look at M1, and this case you look at M2. So what happened around the M1 and M2 particle? If you break down the M1, so what you see the force or the resultant force acting on the M1 mass, like this, right? With this acting is like on this boundary, M1 is pushing forward to M2. This is caused another resultant that M2 pushing M1 as well. So this is pushing backward. So this is what we call P21, because mass 2 pushing mass 1, and this is P12, that mass 1 pushing mass 2. So when you break down this system, on the x-axis, not only F pushing forward, you see P21 also pushing backward. But with this system moving with acceleration, so this net force with the mass is have some acceleration over here, and this also have the same direction of acceleration. You have the whole system moving on the right wayward. If you break into individual one, it should moving in the same direction with the same acceleration with the whole system. This is what happened in the x-axis. How about the y-axis? Because particle not moving upward or downward, you have mg equal to normal force that keep this particle stay on the ground, on table like this. So what about the free body diagram of the particle only M2? As it stated, you have the P12 pushing M2 mass. So here, rather than the resultant force, because the resultant force is not the contact force around here, we look only on the contact force in this system. So rather than you have F, you have P12 over here pushing this object, right? And this object moving forward with the acceleration A. Also have the mg of the mass 2 equal to normal force of N2 as well. With this system, when you see the particle moving with acceleration, I remind you that thinking about the second law of Newton, sigma F equal to ma. If you look after all, this system is moving along only x axis, so you determine only x components. So that means you have sigma fx equal to ma. Whether you look after the whole system, for the mass m1 or m2 is all working around this second law of Newton's. Second laws of motion, or Newton's second laws. Since you know that, okay, you're going to use this for derive and finding the magnitude of acceleration of the system. So now you can use the whole system and look after the resultant force acting to the mass as the second law of Newton to derive this part. So what the resultant force happened here in the first system? So you from the free body diagram of the whole system, you get sigma fx, which is your f equal to ma, and m this case is total m is m1 plus m2. From now you can determine acceleration in terms of the force that you use. So the acceleration of the whole system is force over m1 plus m2. This is how you can use for determine the acceleration. With this system, you can look after another system as well. First of all, like from free body diagram of m1 of number 2. This is the mass m1. What you have seen here, your sigma f equal to ma as sigma f x equal to ma. What you get is f minus p21 equal to m1a, and already known that a is equal to this term, so we can further investigate all other parameters. Like if you would like to determine the magnitude of the contact force here, the second line, that what you would like to determine, you would like to determine P21 or P12. You can determine where this relation. So now if you look after only free body of the mass m1, rearrange this term, you will see the P21 equal to F that minus M1A, right? You change this to another side and have this plus sign and change to the minus sign. You have this term. So you sub the acceleration in, which is you already know the the A already. This is your acceleration of whole system, right? Which is this A equal to each individual A. The system drive with the same acceleration here, right? So now I forgot the unit is meter per second square. So with this substitution, you have P21 equal to F minus m1, and A is F over m1 plus m2. So you can rearrange this term and easily find that the the P21, which is equal to P12, you have I will show you here. When you would like to do a subtraction, you have to have the same ratio. This is going to be your m1 plus m2 f and minus with m1f over m1 plus m2, and your m1 here is gone. So your P21, if you not mind, I will write down here. Your P21 is equal to m2f over m1 plus m2. If you would like to determine the P12, you already know that P21 is equal to P12 if you consider only the magnitude of it. So here they would like to consider about the magnitude. So this is P21, also P12 as well. So this is the force that these two particles contact to each other. So that force have unit in newtons. And this is how you derive the first one, the acceleration of the whole system, and the second one, the contact force between two boxes. When they have a force that acting and looking this system as a two-particle system, right? If we already know the parameters or the constant, we can sub the mass of the m1 and m2 in. If we know the force, we can find the force, and sub in, we can find the acceleration of the system and also the contact force.